Hello. I did my CS231 project in two parts. The first was depth estimation from single images, and the second was using depth data to improve image segmentation. So the objectives were that we capture a lot of image and video data. Images take the 3D scene from the world and compress that into 2D. During this transformation, depth information is lost. As humans, we have the innate ability to infer depth even when looking at 2D photographs. Um, but machines don't have this ability, and this depth is actually quite useful when you get to tasks like self-driving cars and robotics. So that's why I wanted to understand how depth can be estimated from single images. Um, as a second part, I came across some research that showed that inclusion of depth data along with RGB data can improve performance on computer vision tasks like image segmentation or style transfer, etc. So I want to this show that or explore how depth can be added and how it improves image segmentation results. For both parts of the dataset, I use New York University depth dataset. It has a huge repository of images with their corresponding depth map. And so I used a 50,000 sample to train the depth estimation model. It also has a very small set of 1,500 images where it has image data, depth data, and densely annotated segmentation data with 37 classes. So this small subset was used to experiment with how RGBD data can improve segmentation results. Now talking about the modeling approach, I built for the depth estimation model, I used an encoder decoder model with a DenseNet 169 backbone. The encoder and the decoder were very standard, where they kind of have this U shape with corresponding layers, and feature maps between them were concatenated. I experimented with different backbone models like DenseNet 121, DenseNet 169, and DenseNet 50, and found that DenseNet 169 performed the best. It had a relative depth error of 0.128 and RMSE error of 0.474, which were both state of the art. I also tested the model on out of sample and saw that it performed well. The RGBD segmentation model uses, again, an encoder decoder architecture, but it uses to incorporate depth information, it uses two different encoders. It uses an encoder for RGB and an encoder for depth, which are very similar. And during various stages of encoding process, it kind of combines the feature maps from both. Then it uses a single decoder. So with this, I experimented a lot. I experimented with how the accuracy would be with just RGB, with just depth, with depth added channel wise to RGB, with different ways of combining the encoded data. And I found that I got the best performance when we had two encoders, one for RGB and one for depth. And the feature maps were element wise added at the end of each encoder block. This model was trained on a limited set of, as I mentioned, 1,500 images. And it got to an intersection over union score of 0.27. The good observation here was that inclusion of depth resulted in 7% increase in segmentation accuracy compared to just using RGB data. And qualitatively as well, it showed distinct increase in performance in cases where the depth information was very valuable. So overall, it was a very good learning model. In terms of kind of next steps, I would love to train the segmentation model on a bigger data set and look at sort of weighted addition of image and depth features. Thank you.